Thank you. And I would like to start with thanking organizers for such an astonishingly interesting conference. When I was flying here, one person was sitting nearby, and you have 7 hours flight. So he asked what I'm doing for a living, and short answer, I'm a professor at university, did not work. So I had to explain a little bit of what I was doing. And it was pretty basic stuff from textbook on linear algebra. And his reaction was, wow, I have never expected that mathematics is so interesting. Right now, after all those beautiful talks, I'm in his shoes. I have never expecting mathematics is such amazing and diverse subject. So thank you once for inviting me.
You never say too loud that it's very interesting because we stop paying.
That's true.
You are in pain, you suffer, you are pain and compensate. That's strategy.
Yeah. So I would like to talk about one project for which I'm only tangentially related. So you see my only contribution to the whole project. Everything else has been done by different people. So it is started by work of, by the question of Sergei Tabachnikov. It is based on the results obtained by Sergei, Dmitry Borisovich Fuchs, Ivan Izmestiev, Emmanuel Zuckerman, many others. And some of the results will come with some explanation. And this most of the explanations are due to, I believe, genius way of solving problems, of finding explanations to some phenomena. If you have observed some phenomena and you don't know how to explain it, you have to email Anton Izosimov and ask him for the explanation, and he will provide you immediately. So, why it's not working? Okay. So I will start first with the problem which I was interested in for a couple of years. This is called orthogonal ideal polygons. So what is it? If you will start with ideal polygon in the hyperbolic plane with the vertices on the absolute, so the blue one, you could ask for the following question: is there any another ideal polygon such that its respective sides are orthogonal to the sides of the blue one? So right now you could see that red polygon and blue polygon are orthogonal polygons. What do I mean by this? I don't know where is the horizontal. Yes. So this side of the red polygon is orthogonal to this side of the blue one. And then, no, I'm sorry, maybe let's do with the long one. So this long side of red polygon is orthogonal to the short side of blue polygon. Then next side is orthogonal to the next side of the blue polygon, and so on and so forth. So indeed, there exists such object, and what is interesting, for any ideal polygon, well, generic ideal polygon, you would construct, by ideal polygon, I mean polygon in the hyperbolic plane with the vertices on the absolute. All the angles are zero, and all only respective sides. Yes. And it turns out that for generic blue polygon, there would be two orthogonal ones, or 0, or 1, or infinitely many. Yes, for generic, so typical situation, it would be 2. And certainly the arcs are complicated to draw. So let's switch to the Klein model of the hyperbolic plane. So now my sides would be just straight lines, but now the orthogonality is something which I have to explain. So it turns out that if you will take the polar lines to the vertices of ideal polygon, they will intersect at the point which is called polar to the side of this polygon. And then if you take any point on the absolute and connect it with the polar to the side, then this line will be orthogonal to the. So how to construct pair of orthogonal polygons? You will play the following game. You will start with some point, with arbitrary point on the absolute, connect it to the point polar to that side. You find the second point of intersection of this red line with the absolute. Then connect it to the polar to the second side of your polygon. Continue this construction and pray to finish in 5 steps. Most of the time, this red line will not close up, but for some very fortunate initial choice of that initial point, it will close up after 5. Well, so this is pentagon after 5 iterations. Well, a little bit about history. The earliest appearance of that particular problem and of that particular model I have found in drawing is due to Gauss. And after that, the next drawing I saw of that kind was due to Oleg Bogayevlensky when they describe some cosmological models, which I do not understand. So it turns out that this transformation is somehow related. So this is a one-dimensional transformation. If you're talking about CP1, it is somehow related to the Gauss map on the unit interval, and you take the fractional part of 1 over x. So this is kind of finite analog of this famous transformation. So a few years ago, Sergey and Dmitry Borisovich and Vanya start to focus on this system. And so I need to introduce some notations. So it turns out that the angle between two lines in this hyperbolic geometry can be related to the cross ratio of 4 points, 4 endpoints of those lines on the absolute. And then 2 lines being orthogonal mean that this cross ratio has to be -1 if you will choose particular convention on the cross ratio. But we could consider the generalized system of that kind, allowing this cross ratio to be fixed to some constant, not necessarily -1. And then those respective lines won't be orthogonal, they will have constant angle between them. But you again can play the same game, ask whether or not there are not orthogonal, but is somehow related polygons. And indeed, it turns out that generically you would get exactly 2 such objects. So you could ask the questions about this relation, what is shared by those 2 polygons which are orthogonal or have fixed angle between sides. And it turns out that this system is, well, this relation is completely integrable in Liouville sense. So I could just tell you. So it says that P and Q are orthogonal if and only if this cross ratio, so the cross ratio PI QI, PI plus 1, QI plus 1 is equal to -1 for all I. Yeah, but this is only one line which is missing. Maybe not only one line which is missing here. No, it's hard. I have to. Oh, okay. But whatever, still the line is missing. So it turns out that this relation has a lot of conserved quantities, and they are in evolution with respect to some Poisson structure. But I will not dwell on this today. And then let me describe you the bicycle correspondence. It already appeared this morning. So this correspondence was studied by Sergey and his PhD student, probably, no, just postdoc, undergraduate student, a while ago. So you could consider, again, polygons just on Euclidean plane. They're not hyperbolic anymore. And you would say that two polygons are in bicycle correspondence. Well, it is written here. So if lengths of sides, respective sides, are the same, and the distance between vertices Pi and Qi is fixed to be some constant. So there is one parametric family of those. You could change this length of the bicycle. So this C, you provide many different polygons in this C relation. And again, it turned out that this relation is completely integrable in the sense of Liouville and Arnold with another Arnold. All right, and it turns out that the conserved quantities of bicycle bicycle correspondence are shared with Adler's three-cutting transformation on the Euclidean polygons, which has been, fortunately, luckily already described to you by Anton today. And you kind of can see why they are so closely related. It's basically the same type of relation between the polygon P and its three-cutting. You would see this trapezoid. Okay, so now let's start the actual talk. So it turns out, so we have this ideal hyperbolic situation when we have correspondence. We had the integrals. I will explain how they arise. And there are some additional integrals of this relation. And on the other hand, we have Euclidean story, which has bicycle correspondence, having also huge amount of conserved quantities. It has something, some other transformation, group of transformations related to it, which is Adler recutting. Integrals, well, so in the Adler paper, come from Veselov, Shabbat dressing chain, and also this additional integrals appeared there as well, and this is so-called circumcenter of masses for the polygon. Yeah. So then 2 years ago, Sergey appeared and said that there is a low-hanging fruit of extending ideal situation to also some hyperbolic geometric setting with just a little twist. Well, not that twist, some small tweak. And after 2 years, we finally found partial answer, well, kind of partial partially harvest this low-hanging modulo. So we're still waiting for Anton to provide us independence of our integrals. Okay, so I will try to explain what do I mean by centroaffine polygons, what do I mean by serialization, what do I mean by centroaffine recutting, how you could find integrals, and how you would find the additional integrals of this correspondence. So what is the centroaffine polygon? Those would be polygons in two-dimensional Euclidean plane, but I will fix an origin in the plane. This is letter O here, and it will be always denoted with the small yellow dot. And I would consider on the plane modulo some equivalence relation, but this equivalence relation won't be just translation, rotation, and scaling. I will allow any SL2 action on all vertices. So I could just take any SL2 matrix and apply it to all those vectors, P1, P2, P2. Right? So those two polygons will be the same for me from my point of view. So this is the centroaffine polygon I will talk about. So then what? Yes, so you consider set of polygons. No, translation, sorry, no, translations are not, no. Yes, SL2 action. So, yeah, but so it's a diagonal action. So I take one matrix and act, yeah. And then what is the notion for the correspondence in polygon? Well, determinant of the matrix formed by two vectors will be fixed. So this is a well-defined notion. So if I would have two polygons such that for any j determinant of this 2 by 2 matrix is fixed to be some constant, I will say that my polygons are in centroaffine serialization. Okay. And here is the picture how you could actually draw such pairs of pentagons. You could also draw a pair of hexagons or quadrilaterals or so on. Okay, and it turns out that this, so for generic n-gon, oh yeah, sorry, yes, sorry, all the side determinants are fixed. So side determinants is +1 has to be equal to determinant j +1. So it's a complete analog of of bicycle correspondence, but now I just replace. Well, I could actually write the same condition, but that would mean determinant now. Yeah. Oh yeah, thank you for asking. This is a way to construct pairs of serialated polygons. You start with some artificial polygon A, and then draw the lines through the origins through the center of the sides of A. Then if you will take any point P1 and take a centroaffine reflection in this line, so that means that P4, well, there's P1, P1 is somewhere. Okay, so P4 to that point has to be equal to the distance from that point to Q 5, and this line has to be parallel to the side of F4. So then, if you will do this 5 and then 5 more reflections, you will obtain 10 points, and every odd one will correspond to the vertices of one polygon, and every even one will correspond to the vertices of that one. You can do that. You can do that, but you see the parameter C, which depends on the initial choice of. Yeah, you could do that. Yes. All right. And then there is a centroaffine version of Adler recutting. You do this affine reflection with of J's vertex of the polygon, and you will obtain this elementary centroaffine recutting of the original one, and then you could. So in Adler paper, he considered not the whole group of these elementary cuttings, but he provides the composition of elementary cuttings in first vertex, and second, and the third one. Then so it's a cyclic transformation. And here I just draw you the centroaffine version of it for the triangle. All right. So the statement of the result is that centroaffine version of bicycle transformation and centroaffine version of Adler recutting are also completely integrable. They have enough integrals in involution with some Poisson bracket, which I will not present today. But the source of the integrals I will certainly talk about. And let me briefly describe how the integrals for cross-ratio dynamics appear. So what you have to do, you have to consider a loxodromy with any spectral parameter lambda along the line in hyperbolic plane. So you fix any parameter lambda and consider a skew motion in the hyperbolic plane along this line. So you have a hyperbolic translation with the unit speed or lambda speed rotation around the axis. This will be called loxodromy. It will be denoted with L, with parameter lambda corresponding to the skew parameter, and P and Q will correspond to the endpoints of the line you're considering. And then it turns out that for any Z in projective line or plane, it turns out that the cross ratio of points P, Q, Z and its image under the loxodromy will be always equal to 1/1. So if this is true, you could associate the corresponding matrix for this transformation. This would be very nice matrix depending on parameter lambda and parameters P and Q. So now for given polygon, you could consider the composition of those transformations along the sides. This will correspond to the product of those matrices. So that it would be 2 by 2 matrix with entries depending on the parameter lambda. And it turns out that for C-related polygons, those matrices are conjugate. Therefore, you could consider the and determinant of this matrix, compose some nice function out of it, and it turns out that this Yeah. So, and it turns out that if P and Q are alpha related, then those matrices are conjugated with that parameter. And therefore, this expression is invariant under alpha relation, and therefore you could consider, so it's a polynomial in lambda, and you could consider the coefficients of this polynomial, and all those coefficients will provide you conserved quantities. But then this is an annoying part of the story. You have to show that those functions are actually independent, but this can be done by some magic machinery, which I would not describe. But so, yeah, here it is. But it turns out that C relation on, well, alpha relation on the ideal polygons have three more quantities and has some pre-symplectic to form on some space. So, and well, those sort of quantities are fairly easy to compute if you know the coordinates of the ideal polygons. They have really nice formula, and they come from some other magic machinery. And then Ivan Izmestiev come up with very nice geometric description of those three integrals. Well, I can try to explain in a moment. So you could bake up coordinates of a point in hyperbolic plane out of those three conserved quantities, plus one additional real number. And those coordinates of the point on the hyperbolic plane will be the coordinates of barycenter of hyperbolic polygon. This is the point minimizing the sum of the square of hyperbolic signs of the distances from the point to the sides of the hyperbolic polygon. Yes. Well, so as Anton already explained, unfortunately, all this come with this annoying construction. You start with the closed polygons, then you have to consider twisted polygons. So it's a periodic sequence of, so it's a sequence of points in P1 such that Pi plus n is equal to some monogamy matrix multiplied by Pi. And the closed polygons are those for which if you will consider something on twisted polygons, then there is a monogamy matrix involved, but here is just modulo n. Yes, this one, but all the previous formulas does. Okay. How much time is left? 15 minutes. Okay, thank you. So now it turns out that for centrifying polygons, you could do more or less the same trick, but now you have to replace cross ratios with the determinants of the corresponding vectors. So you have to come up with the nice coordinate chart for the centroaffine polygon, and the coordinate chart provided by pairs of numbers. So those are side coordinates. So for each side of the polygon spanned by the vertices Pi minus 1 and Pi, we will denote by S2i minus 1 to be the determinant of those two vectors. And how could you remember those strange? So they all will be odd indices for those S. How would you memorize it? The mnemonic rule will be the following: just add those two indices, and you would get mix of S. And for the short diagonals of the polygon, you could consider the determinant of the vectors pi minus 1 and pi plus 1. This will provide you v with, so the second coordinate, which we will denote by v because it's for the vertex, and it would always have even index, and add those two, you will get to 1. That's the mnemonic rule. And then, since our polygons are in plane, there is a nice linear relation between vectors pi plus 1, pi minus 1, and pi with some coefficients. So you could consider this as a recurrence relation on the vector pi plus 1. You could express pi plus 1 through the vectors pi and pi minus 1. Okay, so now you could start with vector p1 and vector p2, construct vector p3, then p4, and so on and so forth. How would you do that? Well, you would multiply some in some basis vectors by the composition of those 2 by 2 matrices. This is called monogamy matrix. So if you will look for the closed polygons, then you would like this matrix after n steps to be just an identity matrix. You would like to get back P1. So you just have to multiply a bunch of 2 by 2 matrices, and it turns out that there is a combinatorial rule how to do it without actually multiplying n matrices together. So you could just compute the elements of this matrix Mn if you know how to compute the determinants of the matrices of that kind. Well, I believe people did not know how to compute determinants of that matrix until New Year, probably maybe, or until earlier. But nowadays, the most intriguing way to compute such determinants is due to Lewis Carroll, Charles Dodgson. So you could condensate matrix, compute determinants of smaller and smaller matrices. And this is somehow related to the freeze patterns and cluster stuff, which I don't want to touch today. Okay, but so all this being said, you just can compute all those elements, and you know that if you want your polygon to be closed, then you need to satisfy this condition. Okay, so now if you have closed polygon P, you can start with test vector Q1. And so you would like to construct polygon Q, which is C related to the polygon P in centroaffine version. How to do that? Well, you have so many conditions to satisfy. So again, you could construct some 2 by 2 matrix providing Q2 in terms of P and Q1. Then you could construct Q3, then you could construct Q4. You pray for this trajectory to close up after n iterations. Again, how you would do that? Well, there are only 2 by 2 matrices which will relate, which will depend on this parameter C and the polygon P. You would multiply again those matrices all together. At the end, you would get some 2 by 2 matrix. You would like this matrix to be identity. And so you just compute this, the elements of this matrix, and for given in order for this matrix to be identity, it will provide you the conditions on Q1, and those would be just quadratic equations for the components of Q1. So the quadratic equation has either 2 or 1 or 0 or infinitely many solutions depending on the coefficients, but generically it would have 2. All right, and then again the very same theorem holds. If you have 2 C-related centroaffine polygons, then the corresponding Lax transformation along the sides of one polygon and along the sides of the other polygon are conjugated. Therefore, you could compute again the same ratio. It's well-defined invariant. So for any parameter lambda, and then again the coefficients of this polygon will provide you enough invariance if you believe that Anton will prove for you the independence. All right, and it turns out that again the same mysterious machinery will provide you 3 additional integrals for this relation. Yeah, and I forgot to say that all those invariants are invariant not only of centroaffine C relation, but also are invariant under any elementary centroaffine recutting as well. And then you could compute again those 3 numbers, but now we don't know any minimizing property of geometric construction which you could bake out of those 3 numbers, but somehow we can associate those 3 numbers to some geometric construction, which would be called well, I don't know better name for it, circumconic of not masses anymore, something else. So if you will consider the conic with those coefficients appearing from the polygon P, this conic is invariant under centroaffine recutting and well equal to 1 or area of the polygon if you wish, or some constant. But so yes, this geometric object is preserved, but well, at least I don't know any optimal properties of this geometric object, as well as I don't know any optimal properties of the circumcenter of masses for the moment. Okay, so now let me just show you some pictures, which so the proofs of those elementary geometry theorems. There are conceptual proofs coming from the integrability of the centroaffine relation, but actually you could prove it by means of planar geometry. So picture words, sound of words. I don't have time to present you all 1,000 words describing that particular picture. 5 minutes. Oh, thank you. But it turns out that if you have polygons P, Q, and R such that P is alpha is A related to Q and B related to R, then there exists another polygon S which is A related to R and B related to Q. And you could spot the corresponding sides of those polygons on this beautiful picture. And so basically, this theorem can be formulated as follows, that some midpoints of some intervals and the intersection of diagonals of some trapezoids all pass through the origin. Another nice result of the same flavor it turns out that elementary centroaffine recuttings satisfy braid relation or relation of affine symmetric group, as Anton already explained. But again, you could just spot it through this very elementary picture. So it's all about some trapezoids, some points of intersection of diagonals, and so on. And finally, it turns out that elementary recutting commutes with C relation, and this is an explanation. You could clearly see that this is true. So sometimes picture works, sometimes it does not. And for the circumconic, which I have described, it turns out that circumconic for quadrilaterals and for triangles have some geometric meaning. So it turns out that for any quadrilateral, there exist two homothetic central conics, such that even sides of any quadrilateral belong to, of P, for example, belong to one conic, and odd sides belong to another. And then centroaffine recutting preserve this structure. So if you will consider the centroaffine recutting of the polygon, it would get exactly the same structure. Its even vertices will belong to one conic, and odd vertices will belong to another. For triangle, it's better. Triangle determines central conic uniquely, and centroaffine recutting of triangle will belong to the same central conic, as well as C-related versions. Okay, so then there is fancier language to promoting that actually it's not just planar geometry, but I will skip it. And another picture I would like to show you. It turns out that if I will fix the polygon P, I could consider the set of all values of parameter C for which there is a C-related polygon. And it turns out that for not all values of C, such polygon exists, and for particular polygon P, which corresponds to the variables V being 1, 3, 5, 7, and 9, this is it for the pentagon, the shaded regions of C does not contain C-related polygons. And you could see that those are strange, probably algebraic curves, which are tangent to the vertical lines exactly at the points 1, 3, 5, 7, and 9. And I believe this is a result by Dmitry Borisovich Fuchs. I don't know. Well, so those red shaded areas is the areas where discriminant of the discriminant is negative. So there is some quadratic equation. You could compute the discriminant of it. It appears to be quadratic in some other parameter. So you compute discriminant of the discriminant. It's again quadratic in some third parameter. You compute discriminant of the discriminant. And if this discriminant is negative, it's exactly those shaded regions. Yes, 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 yes. K is C is the parameter of C relation. K is the discriminant of this quadratic relation.